The paper of the day is Exploiting Upper and Lower Bounds in Top-Down Query Optimization. System R's bottom-up query optimizer architecture forms the basis of most current commercial database managers. This paper compares the performance of top-down and bottom-up optimizers using the measure of the number of plans generated during optimization. Top-down optimizers are superior according to this measure because they can use upper and lower bounds to avoid generating groups of plans. Early during the optimization of a query, a top-down optimizer can derive upper bounds for the cost of the plans it generates. These bounds are not available to typical bottom-up optimizers since such optimizers generate and cost all subplans before considering larger containing plans. These upper bounds can be combined with lower bounds based solely on logical properties of groups of logically equivalent subqueries to eliminate entire groups of plans from consideration. People implemented such a search strategy in a top-down optimizer called Columbia. Their performance results show that the use of these bounds is quite effective while preserving the optimality of the resulting plans. Looking at the performance analysis, it is difficult to compare the performance of different optimizers. Measures such as elapsed time or memory usage are not comparable unless both optimizers are implemented in the same environment. Opt++ makes a significant contributions in this direction, implementing several approaches within a single framework, but Opt++ reports only the Volcano and not the Cascades or the Columbia search strategies. The Volcano search strategy does not lend itself to pruning. Furthermore, it is not clear that the structure of Opt++ is appropriate for the multi-expressions used in top-down optimizers. They use the measure of number of multi-expressions generated in order to compare bottom-up optimizers such as starbursts with Columbia. Looking at the contributions of this paper, the paper explained the top-down and bottom-up optimizers use the principles of optimality to populate two data structures and pointed out that a key difference is in the order of enumerating the groups. The paper described the search strategy of the Cascades query optimizer and the improvements on the search strategy that we have implemented in a query optimizer called Columbia. Those improvements use upper and lower bounds to implement group pruning, a method for avoiding the generation and testing of candidate multi-expressions that cannot participate in an optimal solution. Such bounds are not available to bottom-up optimizers, such as starburst. Paper has proven that any connected cyclic query can be optimized in such a way that cheap upper bounds are likely to be obtained early in the optimization process. Paper described the performance characteristics of Columbia compared to the bottom-up optimizers such as starbursts. They consider chain and star queries with varying number of tables and varying cardinalities. For multi-expressions generated, top-down optimizers have the potential to outperform bottom-up optimizers. Now let's look at the PS score for this paper. Overall, this paper is a decent read, so it gets 8 out of 10 on readability. With 14 pages long, it gets 8 out of 10 on length. It's a prototype and measurement paper with good description, so that makes it 9 out of 10. In this industry value and learning meter is decent, so it gets 8 out of 10 on each. Overall PS score is 8 out of 10.